effective science labs compatible with next-generation science standards. Before we get started, I'd like to go over a few housekeeping issues. You have joined this webinar in listen-only mode. You will be able to hear the presenters, but due to our size today, we won't be able to open up our microphones to hear you. However, that doesn't mean you cannot participate. We will be offering several chances to interact with questioning. If you look on the right side of your screen, you will see a questions area. If you'd like to answer a question, please type it in here and we'll collect all questions to answer at the end. We will also use this feature a couple of times throughout the webinar to share your thoughts on some discussion topics. For those of you interested in receiving continuing education credits, we can offer evidence of attendance for those participants who stay with us throughout the duration of the webinar and take the survey, which will be sent to you through an email after this webinar. The proof of participation will also be sent through email. I'd like to introduce Julie Olson. Julie Olson has been teaching high school science for 24 years. She is an adjunct professor of biology for Dakota Wesleyan University, as well as Northern State University. Mrs. Olson is a current Society for Science and the Public Fellow, South Dakota Outstanding Biology Teacher Award Rotary Teacher, and 2007 Presidential Awardee for Excellence in Science Teaching. Mrs. Olson is very involved in science throughout the state with participation in initiatives such as Curriculum Development for Science on the Move, a mobile science lab, and the James Project, a statewide water quality project. She currently serves as the co-chair for the NCA North Central Accreditation Review for her school, as well as Science Department Chair, Principal's Leadership Team, Principal's Cabinet, and the Science Curriculum Review Chair. She lives in Mitchell, South Dakota with her husband Mel and 2 college-age children. Julie, we are so glad to have you here with us. Let's get started with the presentation.
Well, thank you. And welcome to everybody for joining this webinar. Today's webinar is, again, creating effective science labs compatible with the next generation science standards. Today, we hope to learn how to use the performance expectations and their foundational components to analyze current labs and activities that you use for compatibility with the NGSS, how to modify existing labs and activities for greater compatibility with NGSS, how to incorporate multiple practice activities, and analyze forthcoming materials for NGSS coherence. So let's start off with a poll right now. How many of your current labs and activities do you think you are going to have to throw out when adopting the NGSS? With all of them starting from scratch, keeping them all, they work then, they will work now, throughout only the short activities for deeper thinking ones, or it depends on how they align in their purpose. So you have the polling, and we'll get everybody's views on this. All right, so we had great participation in that, and hopefully, everybody's finding that this is a pretty good way to interact and get your thoughts out there initially. Well, let's look at our choices here. Throwing out all of them, many activities are very good and serve as a basis for some level of instruction, be it engaging, exploring, explaining, expressing thoughts, elaborating, or evaluating what the students know. The key will be to have students discuss their findings in some way. That can be speaking, writing, drawing, depending on their skill level, but always with the intent of extending that learning to a higher level. Not all activities are probably going to be usable due to time constraints, subject matter, or depth of student investigation related to purpose. Implementing the NGSS is going to take more time. They concentrate on depth over breadth. A recent article in Ed Week says students and the teachers need time to talk. We're talking about discussing, debating, arguing. You're going to hear more about those practices. And so these short activities that we commonly use, yes, the awe-inspiring demonstrations, the discrepant events, they're going to serve to initiate discussion, engage students. It's going to start that first practice that we're going to learn about or that you already know about called asking questions. So what are our shifts? We have the old National Science Education Standards, and everything was pretty much set in separate categories. We had the unifying concepts and science's inquiry. Now we have these practices, we have engineering, we have applications of science. And so one of the big questions that I commonly hear from people is, where's the scientific method? It's not set off by itself in a separate category, such as with the old science education standards. It is embedded within the performance expectations and tied to the content, the disciplinary core ideas. Engineering practices, which are application of knowledge to solve problems, is also embedded within these standards. We need students to see that this is an integrated approach to gain the ability to transfer knowledge and skills, these practices again, to new situations. One cannot even begin to fathom knowing everything, but we can learn how to approach new situations and seek new information as the situations arise. So let's start off with let's have another poll here. How many times should a practice be used in a curriculum? We have once if a student gets it, as many times as it shows up in the NGSS. Let's pick an average, 5. There isn't enough time to do more than that. Or every time it's applicable to the instructional activities, the more the better. Okay, so it looks like everybody pretty much agrees, and that's great. I'm seeing, what one of the main intents of the NGSS is to practice. And again, we get the idea, practice, doing something over and over, even if you succeed the first time. So we're going to actually look at the practices, and those are going to give us some ways to improve upon current activities that we already do in the classroom. It's also going to give us something to look for in the new activities as well as the old activities. Okay, so asking questions. If we're talking about science, we're talking about defining problems, trying to solve them. Could be, why does this do that? And then having question. This actually is one of the parts of the NGSS. A lot of people have questions about, well, how are we supposed to ask questions? It's actually trying to get the students to ask the questions. The big thing is it testable? Is it something that we can collect data on? Can we debate this? The next one is developing models. These are not just pretty pictures or plastic representations. We've seen the models of the solar system. Well, what can it be used for? Can it be used to test? things can it use to elaborate? Models are not conceptual entities. It can be mathematical equations, such as those used to predict climate or population change. Many of you have had students calculate the slope and equation of a population graph and then use it to predict the population at a future date. That is a mathematical model. Models can be images within the students' heads initially that we want to help them learn how to communicate those, drawing, writing, to others. The next, planning and carrying out investigations. This is what we probably would have referred to in the old standards as the scientific method. The design, depending on the level of the students, would include controlled, independent, and dependent variables, replications, collecting data. So this is not something that's going to be accomplished in one activity. Analyzing and interpreting data, graphs, charts, equations. Raw data makes very little sense until we look for patterns. And patterns, as you're going to recognize, is one of those cross-cutting concepts. Using mathematics and computational thinking. These represent observations of the physical world, measurements, counts, data from sensors, and simulations. Using the digital tools available, such as computers. Creating and defining equations, the slope of the line, statistical analysis, such as average and mean, using some logic, and for our advanced students, calculus. It's a tool for evaluating and communicating their findings. It is used in argumentation. What's your evidence? You will find yourself asking your students that more and more. So again, see the connections developing between the practices. They naturally lead into each other and connect. Constructing explanations. Again, using empirical data to explain how one variable relates to another. Designing solutions. Using test results to evaluate possible solutions or to improve upon them. As an example, water purification problem. After students design their systems and collect data, which is the best and why? They need to have empirical data. Is it acceptable? You need to ask them that, is that water clean enough? Would you drink it? Don't let them, but would they drink it? Why or why not? What's their evidence? What could be improved upon? What are possible sources of error? Adding questions like these that require more than a simple answer are what we're going to be striving for. And this is going to lead into the next one, engaging our evidence. What is their evidence for the arguments they're making? A sense of a new idea or a particular design. Why is my design better than theirs, or vice versa? Or maybe neither of them is acceptable. Students could be asked to defend their design on a water purification system before it is even tested. What, as you're walking around, ask them, why did you decide on those materials or that layering? What's some prior knowledge? And this is going to be giving you an idea of where they're at. Obtaining, evaluating, and communicating information. Read and produce information, written, digital, verbal. Students can utilize those 21st century skills. Some students are not comfortable with some types of communication, so these skills will need to be developed. This is also going to be a great connection to those Common Core state standards. The next part of every performance expectation is cross-cutting concepts. They can be found towards the end of each performance expectation. They further the application across the disciplinary core ideas. Further explanation for each can be found in the foundation to the right at the bottom of the NGSS documents. So quickly going over those, we have patterns. These organize thinking and classification, which includes graphical analysis. So some examples. What are the differences and similarities between monocots and dicots? Give them some actual examples if they're available. Give them pictures. What pattern do you see between the populations of predators and prey? If presented with a new discovered organism, how will they know how to classify it? What are the patterns that they see within whatever group level, kingdoms, phylums, what are the patterns there? Cause and effect. Investigate and explain. When one variable is changed, what is the effect? Looking at your data, what do you predict will happen when we change variable A? Why do they think so? So getting back to the predators and prey, if predators are controlled, what will be the possible effect or effects on the prey? And again, what's your evidence? Scale, proportion, and quantity. This is one that a lot of teachers struggle with. Scientists seem to move so easily between those. And if you think about it, we really don't realize that we're doing it. So examples would be levels of organization, moving from the molecular to the cell, to the tissue, to the organ, even ecosystems of different size. Time, short, fast, long times, and quantities. Are the effects different in predator and prey in small populations or numerous and spread out all over the United States? Which of those examples would show a more pronounced effect? So again, there's a scale and proportion. Another example, is a pollutant's effects more pronounced at a cellular level or an organismal level? Systems and system models. So this is one that we take for granted too. But having students actually define their systems. What are the boundaries? Are we talking about a meadow? Do we include the stream running through it? Or is it a forest complete with human beings living in the area? Energy and matter. The flows, the cycles, conservation. Why do prey numbers have an effect on predator numbers? Why are there less consumers than producers in an ecosystem? What components of the prey are used for what components of the prey used for by the predators? What happens to the waste? A lot of organisms give off heat. Where's that going to? Structure and function. Properties related to how it is formed and works. What structures in the prey enable it to be a good hunter? Can prey evade because of structures or chemicals they produce? So some examples would be eye spots on butterflies, formic acid excreted by ants, the camouflage of stick bugs. And then the final one, stability and change. These are real systems as well as models of systems. If an ecosystem's biotic and abiotic factors remain stable, the populations are stable too. Well, you can still ask them, what's your evidence? Why do you think so? Do you have other questions that are coming up about that ecosystem? What happens if the temperature changes? Disease takes out most of the prey. And then
we do have a quick question from one of the panelists, or Laura is asking that these are, or she is stating wonderful biology examples, but she was also wondering, do you have some chemical examples?
Okay, well, we have a question there about chemical examples, and so, right, chemistry examples, and so with patterns, obviously with the periodic table, there's patterns all over the place. What's the pattern between the reactivity and the number of valence electrons? Cause and effect. What happens if I put more reactant in there? Is there at some point at which the reaction doesn't get faster? So proportion, obviously, you've got your stoichiometry, your balanced equations fit into that. Models, systems, and that. Is the test tube good? That's your system? Are you taking into account the temperature of the environment or anything like that? Structure and function, obviously, if you get into polymers, or you discuss polar and nonpolar molecules, the structure makes a big effect. And then stability and change. You know, if you add more to an equation, you can talk about what happens there, or to a reaction. So hopefully that answers that particular question. But if it still doesn't, or if people want more examples, we can field those as they come up. The disciplinary core ideas are located in the middle of performance expectation. And so taking that predator-prey example that we talked about, we're talking about bring light energy into chemical energy produced by higher organisms, feedback mechanisms as they relate to stability. We can bring in ecosystems, again, those relationships, energy pyramids, which is a mathematical model. We also have mathematical models such as graphs, charts, those population graphs could be showing exponential or linear growth. We could be talking about carrying capacity. We could calculate biodiversity. We could design solutions if we see a population declining and nearing extinction. What are things that we can do? And that's going to get into your engineering. With heredity, we have the relationship between genes and the characteristics passed on to progeny, and why they look similar to the parents. The origin variation, so we have this population. Where did this unique coloring pattern come from? Biological evolution, we have evidence, multiple lines of inheritance. The concept that organisms with advantageous traits are more likely to survive. Do you do all of these at once? No. It is an opportunity to bundle and revisit topics as well as expand on them at other times. And it doesn't mean that if you're a life science teacher that you can't bring in chemistry, that you can't bring in physics, you know, such as sunlight and the electromagnetic spectrum. Okay, so we have another poll here. How many labs would it take to satisfy a performance expectation? One for every PE, which is a performance expectation. 3, 1 for each foundation. Depends on the instructional sequence, or depends on the level of the students and assessment results. Okay, so we have a little more difference of opinion with this particular poll. And so let's talk about those. A performance expectation is used to assess learning and application of knowledge and skills. And yes, a lab could be used as an assessment, but it does have to be unique and separate from the instruction, or it should be. It can bring in components of several performance expectations. So when it talks about 1 for every PE, well, if we're bundling, that might take care of several. So not necessarily A, although it could be. It's just going to take a lot more time. 3, 1 for each foundation. they're written as one PE, and hopefully the assessments are going to, they haven't developed those yet, but there will be one assessment for that PE. A PE will take a sequence of learning steps to accomplish it. And so these are going to, there will be labs and activities that are going to be these learning steps too. So it might take some students a couple of those, and might take students that have some learning disabilities a lot more. Again, it depends on the assessments that the teacher employs. It's also going to take account previous learning, student experiences. If you're using interdisciplinary concepts such as math, what's their level? Do you have to teach them these? Reading, and we don't think about that as much being science teachers, but it is amazing that a lot of students have difficulties reading scientific text. It is a whole new kind of beast. We have speech. There's going to be time for research. So we had this question here before. Do we have to fill out all of our previous activities? And I think as a group we pretty much agreed, and I agree with you, that the answer is no. Again, this is going to depend on time availability and application to the NGSS. A big fear for a lot of teachers that we will have to get rid of all of our previous activities and labs with this adoption. And again, this could not be further from the truth. This could also be very costly, which in times of limited educational funding could be devastating. Teachers have great familiarity with these, and with some analysis and tweaking of procedures, questions, assessment activities, they can meet NGSS standards and expectations. So I think that familiarity is going to be to our advantage. It's just maybe adding a couple of things, maybe a couple of questions. So when deciding whether to use an activity, you have to ask some questions of yourself. Because again, it's going to take a little bit more time if you're actually going to have students design and carry out investigations, if they're going to gather evidence to argue a point. So it's going to take a little bit of time to do that. And so some things, if they don't necessarily fit, if they don't add to the instruction, we might have to let some of those things go. So what practices and cross-cutting concepts can be brought into or are already part of the activity? Ask yourself that. Can you bring in more? It might take just one more question, or you asking for a little deeper thought instead of just a one-word answer. And you also have to be thinking about what level of performance do you expect. We're trying to get more than a simple answer is the big thing here. So when we're looking at our instructional sequence, this is one useful model. There are lots of other models, but this is from the BSCS-5E model. And I think this is very useful to look at when you're looking at an activity. Where would you use it? And so, you have engage, explore, explain, elaborate, and evaluate. And so, as I said, some of those activities can be used for evaluation, but they must be new in the sequence, not necessarily using something that you've used to instruct them. So we're going to look at a PE and a lab here. This is a PE, and hopefully if you're not familiar with the construction of the performance expectations in the NGSS, the websites, if you Google it, are very good, and they are color-coded too. In this one, the blue is a practice. It has engaging in argument from evidence. The black is your disciplinary core idea, which is the cycle of matter as well as energy in chemical processes. And the green is cross-cutting concept systems and system models. Again, this is not to say that only these practices core ideas and cross-cutting concepts can be used in the instructional sequence of teaching related to this PE. Practices need to be practiced over and over. The more connections between learning, the better. It is all going to make it easier to apply their knowledge and skills to new problems and questions. So we're going to look at a specific lab, and this one is actually found in the Glencoe McGraw-Hill Biology Lab Manual. And so I pulled some of the parts of it that do apply. Instead of just observing characteristics and knowing which kingdom mold belong to, use this as a chance to design investigations. Even visit the history of food preservation and communicate information. So you could start off, instead of asking them the questions, have them ask questions that could be testable. How could we determine that for sure? You could ask them that. Do you have an idea? How could we determine that? Why is this growing here? Could it grow somewhere else? Why does it smell? Again, these are all testable questions. Some other parts to this. Okay, so they set it up, and again, following safe lab procedures, interpreting your data, exchange information with another group. What factor had the most effect on mold growth? And again, they're going to start engaging in argumentation. Well, I think temperature. No, I think moisture. No, I think bread. Well, don't accept a one-word answer. Ask them why. What's your evidence? Do you notice any patterns of growth? Maybe there's different kinds of mold growing on the breads. Well, what are they assuming? How do they assume that it's different kinds? Or maybe it's the same kind? Well, again, they can look up evidence from textbooks, online, any resources that you would give them. Can your experiment be used as a model to predict all molds or fungus growth patterns? Some other things, as I mentioned, the history part. So you bring in, well, how did the pioneers keep mold from growing? You know, the salt, the sugar, what limited refrigeration type systems they had with the ice blocks. Today we use chemical preservatives, which would be a case of engineering. Well, now the question would come up, are those preservatives safe? They can look at bread and cooking labels. So here's your Common Core state standards. They might even want to test preservatives. You know, citric acid, that's a pretty safe one that they could test. Vinegar. So, you know, let them set those things up. Let them design those labs. What other things? It's not that systems and system models are not addressed. They are with the design of the experiment. And we're going to have to make these connections at first very apparent to the students. We naturally just flow between some of these things. I myself, I have posters of the practices and posters of the cross-cutting concepts up in my room. It not only serves as a visual reminder to the students, but also to myself to point these things out, to have them ask questions, to myself to ask them questions referring to those. Systems and defining them, models and their uses, applications and limitations. So what is their system? Is it the bread? Is it the bag? Is it the classroom counter? Energy and matter, specifically having the students think about them. Now this is not as critical if you're not intending to teach about energy and matter at this point, but what will it hurt to put in one more question to make a connection? Again, once is not enough, and doing this one activity is not sufficient to satisfy the PE. As an example, if a basketball player only shoots the ball once and happens to make it, are they proficient? I think that we would all agree, no. Here's another one, very common lab activity that we use, microscope, use in care. Mix it up a little. Don't just have them draw representative cells and tissues. Ask them, why do you think onion cells are rectangular shaped and your cheek cells are round? Are there any patterns? What do you think will happen if I put salt water on those cheek cells? And then hypothesize why it happens. Draw a model. Draw where you think things are moving. Here's another idea. Just looking at money under the microscope. They can find the names of the states, the microprinting, the fibers from cotton and linen. And then you can even ask engineering type questions, because this is a real problem that it goes on all the time, and why we constantly change our money. Why would you expect more or less anti-counterfeiting features on a $20 bill? Again, investigating, constructing explanations, communicating. You could also bring in a discussion on the electromagnetic spectrum. Can you use other forms of light? Can you use thicker glass? What's the difference between a cheap microscope and an expensive microscope? The corresponding performance expectation for a microscope lab. Again, that's here. That is evaluate a solution. It's an engineering one, engineering technology. The microscope was engineered, although at first was a case of serendipity, to see things too small for the naked eye. Schools deal with criteria such as cost, which is determined by the various components used to make the scopes. Why don't schools have an electron microscope? You could ask them that. When did they differentiate between bacteria and eukaryotes? It was all this engineering. You're going to find that engineering and science are very closely tied. In this case, an engineered device has helped advance science. And then questions and problems in science cause us to engineer devices to help us. Here's another lab. This one also can be found in the McGraw-Hill lab manual. It uses readily available materials, iodine, potassium iodide solution, the starch solution, and droppers. Don't have them just carry it out and get an answer. Have some things setting out that show them maybe the procedure, but then let them run with it. Is there differences? But you can see how we got making predictions. We have the experiment. We have interpreting data, analyzing the data, and then engaging in argument from evidence. So here is that evaluation part. Maybe we taught them that. We've talked about vitamin C is, at a more advanced level, what's its purpose. You could talk history. You could talk about scurvy. You could have them reading text and stories about that. But what's the difference between fresh and frozen from concentrate? Do vegetables have vitamin C? Can heating or cooling affect vitamin C levels? So again, having them carry out those investigations. So on this one, we don't have a poll. I want you to just look at these, taking into account whether you've done the vitamin C lab or not. But as it was just discussed, which one of these or multiple ones of these do you think fits that? So I'm going to give you just a little bit of time here to read through these, and then we're going to talk about those. Okay, so let's look at A, analyzing major global challenge. Again, vitamin C deficiencies, which are actually tied to collagen production. Why do they add vitamin C to foods? Taste, preservation, and combat vitamin C deficiencies. B, it is a stretch unless you're using it to say how dependent the rest of the body is on collagen production, to literally hold it together. We don't have collagen, and that's one of the things with scurvy. They lose their teeth, they get sores because their body literally loses the ability to hold itself together. So this dependence, if you do study tissues. But it is interesting, and it's going to provide that hook to draw those students in. C, constructing an explanation. Again, how systems of specialized cells within organisms help them perform the essential functions of life. So literally all of these could tie into that activity. Again, it depends on what you want to accomplish and discuss. And if you can't use it to satisfy any of the PEs or to help instruct them, maybe you shouldn't use it. One final type is a dichotomous key. You know, don't just have the students learn how to use one. See if they can make one. You don't have to use anything fancy. Could be their school supplies in their book bag. I just found one the other day on money, using change and bills. So the last things here, what are some further ideas? What can you use, what can you add to your existing labs and activities, or what should you look for in materials? Again, asking questions. What are some testable questions? Again, it has to be testable. You have to be able to test it. So as an example, it was very cold here last winter. We're talking 20, 30 below. I asked the kids, I've got soap bubbles. And I just left it at that, and they start going, well, I wonder what happens if you blow bubbles outside. And so then I go, well, anybody have any other questions? And I let them go try it. Patterns, describe the pattern, not just to say that there is one. Scale. Again, this is a little bit more difficult to wrap your heads around, but once you start doing it, it becomes a lot easier. Is this test tube beaker a good model of what really happens? A couple more additional ones. Could we construct, draw, think of a model that could help explain what is going on? Or to test or predict new parameters. Energy is conserved, so where is it going? Put that on the model. Put it in their drawings. Why are those cells shaped that way? What factors affect the stability of this system? What could upset this balance? And what are the possible effects? What are some possible sources of error? I always put this in every investigation. How could you make it better? And what are your possible sources of error? I'm not saying that they had error, but it also in any science, physics, chemistry, biology, there should be some discussion on how good a measuring instrument is. There's no instrument that they will use in a high school lab that's going to be without error. How many times should we measure? Even what tools should we use? So now we'll open this up to questions. And type your questions in the question panel. If we do not get to your question live, we will follow up personally via email.
I do have a question from Jane. Do you have suggestions for adapting the higher level inquiry practices when you have classroom of students from different grade levels? I teach a marine science class with students from 12th 10th through 12th grade, and it can be very difficult to figure out what I should expect and accept from the different levels.
Okay. First of all, one thing that I gained from attending a workshop just a couple of years ago is, I deal with students of all levels too, and you are correct that it is very difficult to address all their different needs. But the one thing is that somebody told us at a workshop, they said, don't ever discuss what you expect from one student with another student. That, they always said, well, I'll talk about you, but I'm not going to talk about anybody else. Okay, so with asking questions, you might say, well, I want testable questions, and you can't verbally say, I only want one from you and I need 3 from you. Higher level students, you might even want more. During a lab investigation, maybe some students are only going to be able to accomplish one set of trials. I've had students, instead of writing out a procedure, I have them draw it. And then I can take them to the next step and say, okay, let's try to put this in words. Or I'll go and ask them, how many seeds are you going to put in that baggie? Or what tool are you going to measure with? I guess that's where you really have to make yourself circulate around the room. And so even marine science, come up with as many suggestions or differences between these two organisms as you can.
Thank you.
Mm-hmm.
Marcy asks, what is the most useful resource that you have for NGSS and adapting our old standards to the new ones based on concepts?
My most useful resource is that poster of the practices in my classroom. I see that, and it just visually reminds me to just ask the students, just point blank, what's your evidence? Or I remind them, hey, this is a really good, is this a good model of what you think would happen in the human body? That itself, looking, make yourself read through the NGSS. It's going to take a lot of times to actually become very familiar with it. But again, I think the single most is the practices and looking for those within.
All right. I have been getting a lot of comments about others wanting to see certain slides. I'd just like to announce that we are recording this, and this will be available after the webinar is over. So you will be able to go through this webinar again as a recording. The next question I do have is from Maxine, and the question is, for those high schools that are not well resourced for labs, what is your opinion on interactive labs?
I would say that there's a point. I mean, I think they're useful in some respects. The only thing I question with the online labs is it does decrease that error, that natural error that students are going to experience when they maybe grab the wrong measuring device or they don't use it right. There's part of that, but I also see that they do have to have experience with those interactives, because I think that's going to be one of the ways that we're going to, that assessments, national assessments, are actually going to be built around. Like I said, I don't know what assessments that they're making that are out there right now. It could be a combination of actual hand graded, but I think there's going to be some that are online. As a writer for the NGSS, we did take that into consideration, that any of these PEs should not require advanced equipment, high-cost equipment, that it has to be something that's accessible by everybody.
Thank you. Sanis asks, how do you ensure you have a balance between information and exploration?
That's going to be, let's see, you know, like using a microscope, you have to have information. They're not going to know about refraction and, you know, with the microscopes. There's skills and techniques that they have to learn. They're not going to know how to do electrophoresis unless maybe, you know, and here's where those interactives are very good at showing them maybe a process and then take it to the actual items. It's going to depend on formative assessments by the teacher. Is there a gap here? Are they not going as far as I would like them to do? Or are we seeing common mistakes? Well, we're going to have to address that with the students. But that one's a little harder to outright answer.
Thank you. Barb asks, what are some other shifts that you see in lab work performance and assessment?
Let's see. Okay, so on the assessments, I think a lot of these are, I mean, there's obviously going to have to be professional development and a lot of resources out there. I think a lot of places are really concentrating on that. So, you know, rubrics, definitely a rubric type system, because that's going to allow you a broad range of student abilities. And as we said, you know, again, that previous question, having a class of students with lots of different abilities, you know, this student might be able to only reach this level, my higher level students this. I think if it's in the instructional sequences and not the assessment itself, it's going to have to be, I mean, there's nothing wrong with giving the students feedback and saying, can you improve upon this? Can you fix this? Do you have further questions so I can help you make this better? So I think there's going to have to be a lot more formal assessments along the way before the final assessments.
Thank you. We'll take a couple more questions maybe. Christopher asks, what approach or specific resources would you suggest to vertically articulate and align a set of performance expectations of exiting students in each grade in math and science? For example, do you suggest using an understanding by design approach modified to create a continuum of K-12 STEM skill development?
I like the idea of the continuum because, like we said, there's students of all these abilities, and I think we have to address the needs of both ends of the spectrum. And by having that continuum, it gives us an idea where the student is at, what's their next level. So our lower level, our middle students, and our high level students all should be able to progress to an even higher level. So I like the idea of a continuum. But for state assessments and national assessments, and I'm sure that that's where they have that. A lot of the NGSS, they have assessment boundaries. Because again, NGSS is for all students. All students should attain this particular level, this PE. Yes, you are going to have students that go higher, but the national assessments, when they get developed, follow those assessment boundaries.
Thank you very much. Take one last question. Heather asks, how do you encourage students to actually do their own work? My 11th grade students are good at being sneaky about observing what other groups are trying, and then they copy their ideas.
What I've done in my class, because these investigations, you only have limited supplies and space and time, and so I pair students up and they work on the investigations, designing them. They collect the data, and I make sure that they all collect it. But each student has to do their own conclusions. Every single one of them has to do their own set of conclusions. Or if it's drawing a model, I might say, well, you have to draw a model, you have to draw a model. Again, that's that paperwork part, that the bookkeeping part of teaching that does take up our time. But I think with this, though, the students are going to be so engaged because they feel like they have some control over this. They have input. They are designing them. And so I found that the discipline problems drop significantly, and the students they have their own experiment to do. If I'm walking around, I go, okay, well, so-and-so is doing this already. Could you put a little bit of a twist on this? Maybe it's because they're just not comfortable with their skills yet. So, maybe, well, what are some ideas? Okay, let's do this then. Just getting them excited about it.
Thank you so much, Julie. If you'd be willing to forward to the next slide that shows the webinars at mheducation.com. We'd like to thank everyone for attending this webinar today, and a survey will pop out at the end of this webinar. We are so grateful for your feedback so we can improve the experience for future webinars. You will receive a follow-up email containing a recording of today's session and evidence of your participation, which you may use towards continuing education units or CEUs. If you have any additional questions, feel free to email webinars at mheducation.com. You can learn more about the next generation standards at mheonline.com/NGSS. Have a great evening, everyone. Thanks for attending.